Okay, so here we are with one last example. This is another classic problem, inclined plane with a pulley, and one object has friction between the inclined plane and the object itself, and the other one doesn't. But let's see what this problem calls or gives you, and then we're gonna focus on that. So suppose the coefficient of kinetic friction between the mass A. So I'm gonna call this mu K. Well, we can call it mu Ka or simply mu K since the other one does not have a friction. Suppose this is 0.15. All right. And that the two masses are equal. So Ma equals Mb equals 2.7 kilograms. Remember, coefficient means it's adimensional. I'm just going to call this one given here. All right, as the mass MB moves down, I think this is a good clue for you to see where the direction of the acceleration of the system will be. Determine the magnitude of the acceleration of MA and MB, given also the fact that you have theta and the incline being 34 degrees. Okay, so I'm going to put here as to find on part A, you need to find the acceleration of the system, which is nothing else but the acceleration of body A and acceleration of body B. We'll discuss that in a moment, or simply A. And on part B, let's see what you are asked to find on part B. So that was part A. Okay, on part B, what is the smallest value? So essentially, what is the minimum mu K that will keep the system from accelerating? Now, what does that mean? So I'm going to put here mu K min. I shouldn't even call it a mu K, right? It would be a mu static in the end. That will keep the system from accelerating. What does that mean? That means acceleration will be 0. Right? There is no velocity, there is no acceleration, so it will not move. So that is what you need to find. Okay, so for this, same idea like we did before, you really need to focus on in isolating each object here and drawing the free body diagrams first. That's key. However, one important note here, ignore the masses of the pulley, and the pulley is frictionless, and the cord. That means when you are actually isolating this system, right? When you imaginary cut this wire and you imaginary cut this wire, you isolate here each system. And when you draw your free body diagram, you can actually ignore what is happening at the level of the pulley, because the two systems, MA and MB, will be connected through the cord that is in between them. So in other words, if I'm to put here the tension in a wire that gets transmitted right through here and here, those are all equal. And then this is their connection point. So let's focus on how to draw the free body diagrams. So as we learned before, the first thing, it kind of tells you right here, MB moves down. I'm going to even highlight it here with a different color so we pay attention to that. So if that's the case, this is the direction of movement, isn't it? Means that MA will move up. So what are these here? These are your accelerations, right? So the system moves this way. So now that we have that kind of squared away, we can focus on, remember on a free body diagram, acceleration shouldn't be there touching the body, but you can put it around so you can have a sense of what is going on and where the movement is. Yeah? So let's draw the free body diagrams. And we're going to focus on, just let me finish writing this. We're going to be focusing on each element here. So imagine I'm looking at mass B. So here's a dot, the punctiform dot, mass B. I'm also going to look at mass A. Now mass A is in an incline. And I will actually portray it such. You can actually tilt it, but until you actually get good at it, I suggest you leave it like that, because when you start tilting it, you may get confused where the angle is. Okay, so remember the direction when you write this equation, and so is the direction for me, choosing the direction of the positive for your equations is always in the direction of movement. So to me, the movement is down for mass MB. So this is your axis Y. I'm going to consider that as being my positive direction. Let's see what forces do we have. So we have the weight. So here's MB times G as a vector, right, to make it a vector. And then we have the tension in the wire. So F index tension, or you can call it T. Remember, don't get hooked up on how people call it. Just know what it means and write it down. And then when you put it all together, make sure you put your names on each one of them as I talk, okay? So now let's look at your incline plane. Again, let's do a little bit more practice on here. In order to draw the correct free body diagram, remember through the body, you draw the X axis parallel to the plane. Well, it's almost parallel. I think it's good enough for now. I can make that bigger. And then you have the other axis that is perpendicular to it. And that will be the one where you're going to depict the component of the weight. Okay, so now that we have that, here's your weight, always going, let me change this a little bit, towards the center of the earth. So here's your, what body is this, MA? Okay, so here's M index A. So we have MA times G as a vector. Remember, in a free body diagram, you either choose to put the vector itself or its components, but for practice purposes, today we're going to do both, okay? All right, so your angle theta right there. And now let's kind of look at what direction this is going. You know, I'm going to actually pick the acceleration. So remember, for part B there was like that. Now here, our acceleration is going up the hill. It doesn't go down the hill. Meaning that for me, it will be much more advantageous to pick my system of coordinates on the y is going to be perpendicular to the plane, but going up, it's going to be the positive direction. But the x direction, it's going to be on the positive in the direction of the acceleration. That said, now you know the direction of movement. You now know you also have a normal force, right? So the normal force is perpendicular to the surface, yeah, is the reaction of the surface to the body. So let's call this one F normal. Yeah, I'm gonna keep my lowercase right there. All right, and so because it's moving up, the friction force will be parallel to the plane, but opposite to the direction of movement. So here's your friction force vector. Yeah, and what else do we have? Well, we have the tension force. This is your connecting point between the two masses. So here's your F tension. So this is what connects one to the other, and that will allow you to make the equations work for you. And that's it. The only thing that you really have to worry about is the components of the weight. So let's practice that again. So when you are looking at the components of the weight, yes, please remember that you have to find the angle theta first. And so let me go here. And remember, the way you find the angle theta, it's the angles that are congruent, that have corresponding sides perpendicular. So I'm going to look, my original angle theta, it's formed by this base right here, I'm highlighting in yellow. And that, ladies and gentlemen, is perpendicular to your y-axis. So you know that your new angle theta, it's formed by this yellow part that I drew. And then let's make the other one green. So the other part of the angle theta of the plane, I'm highlighting now with green. Yeah, and that is perpendicular to, oh, I'm sorry here. What did I just do? Hold on 1 second. There you go. So my yellow, let me recorrect this. So my yellow here is perpendicular to the weight. And then my green, yeah, my other side is perpendicular to my y-axis. So now you can see my original angle theta was determined by these two sides of my incline, which I colored here with yellow, respectively green. And that means my new angle theta here is this angle. And I just explained why. They have corresponding sides perpendicular to each other, and that's how you find it. Okay, once you find it, you know that you have to decompose the weight. And again, you look in the triangle and you find out How much is each one? The one that is adjacent, remember, the adjacent part, that will be your cosine, and the one that is opposite, that will be your sinus. So in our case, the one on the x-axis or parallel to the plane will be MA G sine of theta. Again, this shouldn't be part of the free body diagram, but it's a good practice for you. Let me fix this a little bit. Maybe make it longer here to match. Okay. And this guy right here, which is adjacent to angle theta, yeah, that is your MA G cosine of theta. Okay, that said, right, you have everything you need in order to write our equations. So let's proceed in doing that. So I am going to start with sum of, so again, remember this is a dynamic equilibrium, and you have to write Newton's second law equations, right? I'm just kind of shortening up the words here, but you got the idea, right? Okay, so let's look at the free body diagram. I'm going to zoom out a bit. Here you go. So the sum of all forces, well, it's only one direction that his is moving, right? On the y for the B mass is equal to, now I'm going to actually put all the forces right away. So let's see what are those. And you know that this will be equal to mass of B times the acceleration of the system. Let's see what this produces. So we have MB times gravitational acceleration minus the tension force. Now that's equal to mass B times acceleration. Done. This is one equation. From here, I can tell you that I will probably most likely focus later to pull out my tension force to move it into my second equation that will be extracted from the inclined plane for the mass A. Okay, so my next one, sum of all forces, so the net force on the x-axis for body A is equal to the mass of body A times the acceleration. Let's see what this one produces. So right now I want you to focus on what is happening here on the x-axis. So you can see on the x-axis, you are going positive with a tension, right? I set up this to be positive. And then you have two components that are negative. One is the MAG sine of theta, and the other one is the friction force. So they will be with a minus, and that is equal to MA times acceleration. So let's write this down. So we have force of tension minus MAG, and now it's going to be sine of theta. Okay, minus the force of friction equals the mass of body A times the acceleration of the system. So as you can see now, I can replace my force of tension with whatever I pull out from equation 1. Let's put some numbers to that. So here's equation 1, here's equation 2. I can even put my dots there so we can stay organized. Okay, so let's see, what do we do next? So now I know that for the direction y for body A, I have another equation. And because the object doesn't fly up the hill, it doesn't just take off and fly upwards, you know that there is no acceleration on the y-axis. So the sum of all forces on the y direction of body A is equal to 0. All right, so this will be my third equation. Let's see what this one conducts to. Okay, so if we look, the only thing we have here going positive is the normal force. The other one is going negative, and the sum of them essentially will be equal to 0. So one is positive, so that is the normal force. The other one was negative, minus MA G cosine of theta, that is equal to 0. So that is equation 3. I'm going to put a 3 right next to it. And last but not least, remember this word, the dynamic equilibrium, and each mass had its own. And then last but not least, you have to bring in what was the definition of the friction force. You know that is defined as mu times normal force. That would be our fourth equation. So in our case, if we're looking at that, force of friction, look at how much is our normal is equal to MAG cosine of theta from equation number 3, right? Let me highlight this with green, let's say. Well, actually, green, let me highlight it with blue just to kind of keep the same color tone here. So my Fn, if I look here and I pull it up from equation 3, Fn is equal to MAG cosine of theta, meaning that your friction will be equal to mu k times Fn is MAG cosine of theta. So by using, this is equation 4, so by using equation 3. Okay, so as you can see, staying organized is key. And please remember, you have to do the same when you do the exams. You don't jump on a calculator and just plug in numbers, okay? You don't get no credit and you don't understand what you're doing. So from here, we pulled out that Fn was MAG cosine of theta. And obviously we plugged it into equation 4. Okay, so now this is all work by substitution, right? So let's see what we can do. If I am looking at equation 1 and 2, because see, they are asking us how much is the acceleration of the system. I can do elimination between 1 and 2, right? Because if I add them, the tension force goes away. And then I can just simply calculate the acceleration. So I'm going to copy equation 1. So actually, I'm going to pull out, I'm just going to copy that. So MB G minus force of tension equals the mass of body B times acceleration of the system. Underneath, I am going to line up equation number 2. But the way I do that, I want to make sure that the elements kind of align under each other. So I'm going to put here my force of tension right underneath minus MA, okay, and index A, G sine of theta, minus my force of friction. So here's the deal for the force of friction. I'm going to highlight it with green. See this force of friction right here? I'm going to replace it with what I got from number 4, right? So just remember that that was key. And the other one was my Fn, right, which I put down here. All right. So now in equation number 2, I am minus force of friction. Well, instead of force of friction, I'm going to put equation 4, which is mu k times the mass of body A, G cosine of theta. Yeah, this is all equal to M index A times acceleration of the system. And so the reason I wrote them underneath each other, because the elimination method, if you remember, right, I'm going to add this on a vertical. If I do that, the idea is to eliminate a term, right? So the idea is when I add them vertically, this negative FT plus positive FT goes away. What you do need to pay attention is where the equal sign is. Make sure you don't just kind of go blindly and add them and mix them up the wrong way. So everything that is left to the equal sign, we're going to put on the left side. Everything that's right from the equal side, we're going to put on there. So let's see what's left. So when you add them vertically, you get the mass of body B times G. I'm done with the first part on the top equation. Let's see from the bottom equation what's left. Minus mass of body A times G times sine of theta. Okay, minus mu K, mass of body A times G times cosine of theta equals to, so now I'm with everything that is on the right side of the equation. So we had mass of body B times A plus mass of body A times A. Great. As you can see here, you cannot just blindly also cross off the ends. They are not equal. Well, they shouldn't be equal. Maybe they give us anything in this problem. They give you that they are equal, but you may have a problem where they are not necessarily equal. So stick to the algebra, okay? Now, one thing that doesn't repeat also is G. So don't just go cross off the G. What is your purpose here? Your purpose here is to isolate A, right? That's your job here, is to find how much is A. So look at all the terms that contain A. They are only on the right side of the equation, right? So you can factor out that. And then you divide by MA plus MB. So let's go ahead and do that. So we have, I'm going to switch the terms now. So what is on the right-hand side of the equal, I'm going to put here on the left, okay? And I'm going to factor out A. MA plus MB. And I want to see if there is anything here that I can factor out nicely. I am looking to see if there is anything in here that I can factor out. And I can factor out G, I believe. Let's see, I'm going to highlight. I kind of like here MA. We can factor that. We can factor the G. Okay, so that's about it. Yeah. So I'm going to put the G all the way in the front because G repeats on all of them. So this is equal to G. Put a bracket right there. Then you have a MB minus. Now I'm going to factor out MA. Now you have parentheses, sine of theta. Plus, because I'm factoring out with a minus in the front, mu k cosine of theta. This is just to have a nicer form of your algebraic formula for acceleration. Okay, so now you're going to divide by, all right, we're going to divide with MA plus MB. So that is at the denominator, and at the numerator, you have this G parentheses MB minus MA sine theta plus mu k cosine of theta. And you know what? Actually, let me show you something. You can write it even better if you put this G in the front nicely, and then just a fraction line right there. And here I'm gonna put this more in the middle. Now, of course, for problems where MA and MB will be different, yeah, you cannot just simplify them. Normally, if they will actually be equal and they tell you it's equal to M, now you can feel free to actually cross them off. When you see them, you just make them M, all right? So let's kind of plug in our numbers now. Plug in numbers. You see how that one is always done at the very end? So don't jump off the calculator as you start. So what do we have? 9.8 times. Let's see what do we have here. So we have 2.7, I believe, minus another 2.7. Okay, sine of, I forgot what theta was. 34, okay. Sine of 34. Make sure your calculator will be set in degrees. So this is 0.15 times cosine of 34. Okay, all divided by 2.7 plus 2.7. It's just that they are all equal, right? And because I'm kind of old-fashioned here, so let me see something. I'm just gonna do this part right here first. And then, so we have here times 2.7 minus whatever, I'm gonna get something there. And then this is a 5.4 on the bottom. Okay, and this other part. Okay. Okay, so here I'm getting 1.8455. So now it's actually easier to deal with this. So this is 0.85 then. Times 0.8. Okay, so I am getting 1.55 meters per second square. I mean, you can round it if you may to 1.6 meters per second square. So here it is. This is the acceleration of each one of the bodies, which is essentially the acceleration of the system. Okay. So let's see what does it say on part B. So now on part B, they ask you what is the smallest mu k that will keep the system from accelerating. Again, what does that mean? It means that the acceleration is 0. So that makes our life kind of easy because we already determined what the acceleration is. So I'm going to zoom out so we can look at that formula, right? So for part B, if the system is not moving, right, velocity is 0. There is no acceleration. Acceleration is 0. So then you can take the formula that you just got, and then we can have a discussion on that. So I'm gonna take that. What was our acceleration? Was G times mass of body B minus mass of body A, sine of theta, plus mu K that you need to find, cosine of theta, all divided by MA plus MB. Now this, ladies and gentlemen, has to be 0. That's the condition. Now let's have a little chat about that, right? So if this guy here is equal to 0, and you look at this, it's a fraction and a number and whatnot, G has a value that's different than 0. So I'm going to put this is different than 0. So who must be 0? That means the product of two numbers is 0 if one of them is 0. So you have no choice, but this big fraction has to be 0. Now, for the fraction to exist and be 0, the denominator cannot be 0, because if the MA plus MB at the bottom is 0, that means it's undefined, right? When you divide with 0, you get infinity. So if this is equal to 0, that means that your numerator has to be equal to 0. So this is what we're going to be focusing on. So for us, this conducts to MB minus MA, parenthesis sine of theta, plus mu K times cosine of theta must be equal to 0, right? So that is what we get out of this. So your goal here is to find mu K, right? So you assume, because it's a different kind of mu K, considering that the acceleration was 0. So let's see, what do we get here? So your job is to isolate that. So we get MB minus MA sine of theta minus MA mu K cosine of theta equals 0. So again, I'm hunting for this guy, yes. Okay, I'm going to move that term to the right, or better said, you add it. So you get MB minus MA sine of theta equals to MA cosine of theta times this mu K. I keep it separate. So now you can see I'm going to divide with MA cosine of theta, and you get your new mu. I'm going to say mu K min, yeah, such as acceleration was 0, yeah, is equal to MB minus MA sine of theta, okay, all divided by MA cosine of theta. And that is the answer for this particular problem. So now that you have everything, you're going to be able to plug in your numbers and get an answer for it, right? So I would say here is the minimum mu such as acceleration is 0. Just don't forget that. Okay, so mu K min is equal to, well, your masses were the same, 2.7 minus 2.7 sine of your 34. Okay, divide by 2.7 times cosine of 34. Okay, let's see, what do we get? I mean, it's easier to, I like this. I'm going to factor out 2.7, 1 minus sine of 34. So you have less mess on a computer, on a calculator. 2.7 cosine of 34. As you can see, this happens only when the masses are equal. Otherwise, you couldn't do this simplification, you know. So now on a calculator, it's easy to just put 1 minus sine of 34 divided by cosine of 34. So mu K min. Let me see what I get very quick. I'm getting 0.5317. Okay, I'm just going to round this to 0.53. But so that's how you actually solve this type of problems. And they are all very classic examples. All right, I hope this helps. And please watch them again and make sure you try to do one by yourself. And of course, your homework. All right, take care.